Hi, and welcome to another video in our statistics series. So, today we'll be taking a look at probability in stats, and this is one of the later chapters in statistics. And it's actually usually one of the ones that people usually have a little bit of trouble with, probably because the basic concepts are not something that teachers tend to go through. They tend to just give you a bunch of questions that you have to do. So in this video, we'll be covering a few different things. So we'll be taking a look at how to actually calculate the probabilities for single events, how to better actually understand Venn diagrams. So that would be stuff like, how do you find the intersection? How do you understand or and how do you understand like the not stuff, so everything which is outside. So I'll just make it a little easier to understand a little bit about how to draw the Venn diagrams, and when it tells you something about it, how to know what's the right part to shade. Apart from that, we'll take a look at mutually exclusive independent events, and this is something which people tend to get mixed up quite a lot, or they're not really sure how to give the definitions for these. So we can take a look at some of that. And finally, we'll end with probably what's the easiest part of the chapter, which will be tree diagrams. So there's not too many subtopics to go through in this video, and hopefully, yeah, everything will make sense as we go through it. So let's get straight into it. So one of the first things we'll take a look at is when we're actually calculating probabilities, there are a bunch of words which you need to be familiar with. So the first one of these is an experiment. So let's start with that, an experiment. So what is an experiment? So an experiment is basically just like a process or something that you can do and keep repeating a bunch of times, and that will give you some sort of outcome. So it's a process which is repeated to give an outcome. So the keyword here really is the word outcome. So an experiment is a process which you repeat and gives you an outcome. An example of an experiment would be you rolling a dice, and when you roll the dice, you might roll a 6, in which case your 6 would be the outcome. So if I had a dice here and I had to roll it, and then I end up getting a 6, the 6 here, that's my outcome, and the experiment was rolling the dice. And you can do that a bunch of times. So if I do that, then this is also known as an event. So an event is a collection of one or more outcomes. So that's the next word you need to know. What is an event? Collection of one or more outcomes. So it could be that I roll the dice like 20 times and I say, okay, what's this event? The event is how many evens did I get when I rolled my dice, or something like that. So that's the next keyword you need to know. So you need to know what an experiment is, you need to know what an event is, and you need to know what an outcome is. So after that, there's only another thing we need to know, which is something called the sample space. And this is something that people tend to get confused with. So sample space is basically all the possible outcomes. So all possible outcomes. And what this means is if we're rolling the dice, we can only roll a 1, 2, 3, 4, 5, or 6. We can't actually roll anything else. So our sample space would be all the numbers between 1 to 6. And that's basically what a sample space is. So every single outcome you could possibly get, that's essentially what your sample space would be. So yeah, so basically what happens is if you look at all your events and each of your events are equally likely, then the probability of one of your events is just the number of outcomes that you have in that event, and you divide that by all your possible outcomes. So that probably sounded really confusing. So let's actually explain what I meant of that. So what I meant is, so I said, where outcomes are equally likely. So if we have our dice again, each side is equally likely. We have a chance of 1/6 of each side being rolled if we had our dice. So the probability of one of the outcomes happening, so probably of any event. So let's say, what is the probability of a 1? Then to do that, all I have to do is I have to do the chance of the event is basically just the number of outcomes I can have of the event. There's only one way I can get the event, divided by 6 different ways I can have it. If I said, what's the probability of a 2, then the probability of 2 would basically be how many ways can I do that? Well, it's 1 over 6 again. So now if I change that question and I said, what is the probability of even numbers? Then how many different ways can I have the outcome occur for even numbers? Well, I could have 2, 4, or 6. So there's 3 ways I could have it out of a total of 6 ways, and each of them are equally likely. So that would give you a half. So essentially all of this stuff is basically how you would kind of start to understand probabilities. And if there's anything you want to get from all of what I've just said, is essentially you don't need to remember all of this completely, you just kind of need to understand the concept. So it's the idea that in stats, when we're doing probabilities, we do an experiment. That experiment will give you some sort of outcome. An event is a collection of those outcomes, and a sample space is all the possible outcomes. So when we're actually doing probabilities, we just kind of want to take a look at something like the event that we're looking for divided by all the possible outcomes which you could have, which is a sample space. So in the sense where we got like a half of the even numbers, it's kind of saying something like, well, I would expect 1, 2, 3, 4, 5, or 6. And for even numbers, then the only way they can get that is 2, 4, 6. So obviously here you can see there's 3 ways you can get even numbers and 6 ways you can get any of the possible outcomes. So that's why your answer is 3 over 6. So that's just like kind of the basics of all of that. And you probably already know this, but basically your probabilities can only be between 0 and 1. So 1 means it's impossible. I know that can never happen. I can't roll a 6-sided dice and roll an 8, for example. That's impossible. And 1 would be certain. So I know 100% if I do some kind of experiment, I 100% know the outcome. So if I roll a dice, I can guarantee the number is definitely either odd or even, because that's the only thing I could possibly do. So usually your probabilities are going to be somewhere in between this range. So don't worry if that was a little bit confusing. Let's clear stuff up by going through a couple of examples. So let's take a look at examples. Let's say I have a random number generator that I have. Well, let's have 2 random number generators. And what these do is they generate me a number between 1 to 4. And the question would be, I use both random number generators, generate numbers, and to find my final answer, I add the numbers. So add both outcomes. So for example, if I had machine 1, and I had machine 2, then if machine 1 gave me 4, machine 2 gave me 2, then my final answer would be 6 because I'd add them up. So that's how my machines work. They just add up all the numbers. And let's say the question was asking you, could you tell me, based on that, how many ways can I get exactly 4? So that's the first part of the question. And the second part would be asking me, how can I get a score which is more or equal to 5? Something like that. So let's start off with how we'd solve this question. So the easiest way to do this would be to draw some sort of diagram over here. So we could basically put in all the different things we could roll. So we could get 1, 2, 3, 4, 1, 2, 3, 4. And then let's add up all the different numbers we could get. This could be machine number 1, and this is machine number 2. So for machine number 1, we get 2, 3, 4, 5. This would be 3, 4, 5, 4, 6, 8, 7, 6, 5, 7, 6, 5 there. So that's what would happen if I added up the numbers. All I did was add up. So 1 plus 1 is 2, 2 plus 2 is 4, 3 plus 2 is 5, like so on. You can see I've just added up the numbers to get these. So now that I've got this, we're trying to figure out how we can get exactly 4. So how many total outcomes are there? So the probability of getting a 4 is equal to something over 16, because there's only 16 possible outcomes. And referring to what you said before, this is actually our sample space. This is all the possible answers we can get. So based on that, we add this up and we get 60 numbers. And how many of our numbers are 4? Well, there's 1, 2, 3. There's only 3 ways. So that becomes 3. So 3 over 16 is the probability of you getting a 4. So then what's the probability of you getting a score which is more or equal to 5? So the probability of the score being, or let's say let's write that like this, score is more than or equal to 5 is equal to, again, there's only 16 different things we can do. However, from these 16, how many of these are more than or equal to 5? So that would be everything over here. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different things. So the answer for this would be 10 over 16. So there's 10 over 16 different ways to do that. And that's a probability of your score being more than or equal to 5. So hopefully that was quite easy to follow and easy to understand. So those are kind of standard questions that you can expect in probability, nothing too difficult. So apart from that, sometimes you might have different kinds of tables in order to answer it. So let's say how long we can say, or let's say how long people spend on average having their lunch, for example. So the average lunch times, and let's say the frequency of that. So let's say our lunch times range between 5 to 7. Then actually, let's actually do this in a way that you can expect in an exam. So we might say lunchtime is equal to t. So let's say your lunch times could be between 5 to 7. Then between 7 and 9. And then between 9 and 11. And then the frequency of each of those was 7, 10, and 11, something like that. So someone said this question and said, okay, based on this question, what is the probability that someone will spend less than 9 minutes? So what's probably t is less than 9 on their lunch? And so yeah, let's figure out how we answer that question. So for something like that, all we really need to do is we have to basically take a look at this and say, okay, for the total frequency, we have 7 plus 10 plus 11. So in total, there are 28 different people who have done this entire thing. So again, our sample space is that's a sample space. And how many of these people are less than 9 minutes? Well, everyone who took 5 minutes to 7 is less than 9. And everyone who took between 7 to 9, since there's I should have had a less than sign here, is also less than 9. No one in this bracket is less than 9, since this is more than or equal to. So basically I only count these two people here. So I do 7 plus 10 up here. And that gives me 17 over 28 people. So that would be the number of people who I can expect to be over in about that kind of time frame. So that's how you can do one type of question. Another question might be, what's the probability that t was less than 10? Now for this one, you can see we don't really have a way of doing 10. And let's just say I change this number slightly. Let's change that to 12 just to make the numbers easier. So if I did something like that, again, there's only 28, or actually not 28 anymore, there's only 29 ways I can do this. Then once I've done that, what ends up happening is these people are less than 10 minutes, these people are less than 10 minutes, but here I've got 9 to 11. So in order to fix that, you can see that 10 is exactly halfway through. So using interpolation, what I'll assume is about 6 of these people count in there. So what I'll do here is I'll say 7 plus 10, but since 10 is only halfway through the third class, then all you can do there is add on the 6. So if you do that, you will get 23 or 29, and that's your probability. So that's kind of how you answer those kinds of questions. So hopefully that kind of made sense. Essentially what you want to do is you want to understand what's your sample space, and then how many ways can the thing that you're trying to get, how can it occur? So here I said in this question, there's 29 different ways that things can occur, because I got that from here. And then I said, well, t is less than 10. Well, that's 7, that's 10, and that's half of that, which is 6. Add them all up, and then get what this part here is. So that's pretty much it. So that's like very basic single event probabilities. Yeah, and that's how you want to kind of understand it. If you want a kind of a way to understand it, you can say the probability of an outcome is equal to the ways you can get the outcome all over the sample space. That will essentially give you the probability. So that's kind of what we've done. So you can go through a few exercises and hopefully all of that will make some sense. Okay, so now let's move on to Venn diagrams. So let's try and understand what exactly is a Venn diagram and what is it used for. So Venn diagrams are basically a nice way for you to represent all these events and stuff on a graph, and it makes it a lot easier because you can put like frequencies, probabilities, and all those things in different parts of a Venn diagram, and they'll tell you different things about it. So you've probably heard of something called the events A and B. And even though in first year stats I don't show you the symbols, I'll show you that anyway. So that would be A and B. That's how we tend to write A and B. And this represents the middle part of the graph where our two circles, this is a circle for A, this is a circle for B. This is where both A and B are occurring, and that's basically where they overlap. So that's what A and B means. It means that if A is occurring here, then B is also occurring here. So just to give you a bit of a way to navigate your way around these graphs. Let's say my event occurred here, then it occurs within A. If it occurs here, it occurs in B. If it occurs here, it's occurred inside A and inside B because it's in both the circles. And if it occurs here, it's in neither A or B because it's in none of the two circles. So yeah, like I was saying that A and B is the intersection. The next thing you need to learn is A or B. A or B. And the sign for that is A, U, B. Again, you only learn that in second year, but I'll show you that now. And this is basically everything which includes A or includes B. So this would be everything. So basically when it's A or B, you just shade all of A, shade all of B, that's it. When it's A and B, you just shade the parts which overlap, like that. So you know if it was A and B and C, something like that, then you'd only shade this middle part. Whereas if it was A or B or C, you would actually shade all of that, and all of that as well. So those are the two. And then there's a final one which you need to know, which is known as the event not A over there, and we tend to call that's how we show that in probability. So not A means basically everything which is not inside A, and that means also this part, because this part outside is not in A either. So that's how this part works. So these are three parts you just need to be kind of familiar with. A and B, A or B, and not A. So yeah, it'll be quite good to show you some examples because there are some word questions which people often get confused with. So I'll show you a few examples of how these work. So let's say we have a question here where it says, I have a class of 40 people where 9 people play football, 5 people play cricket, and 3 people play both. So I want to find the probability of someone who is, what's the probability if I pick a child that they do not play cricket, for example. So not cricket. What's the chance they do not play cricket? That's the first question. And then let's take a look at a question where what's the chance that if I pick someone, they play neither football nor cricket? So then the probability of neither football or cricket. That's the second question. So before we do that, the actual main part of these questions is you just need to fill out this diagram. Once you fill it out, solving the questions is not very difficult. So how can we start? Well, there's 40 people in the class. So we know for sure that 3 people play cricket and football. So that's the only one we can be certain for. So that's the first one that we put in. You always put in the one which is got everything involved in it. The reason I can't put 9 for football here is that, well, if I put 9 for football here, and let's say it happens that 5 people play cricket here, then 9 plus 5 is equal to 14, which is more than the number of people allowed to play football. So that's why you don't just start by putting 9. The 9 here and the 5 here just means that everything in this circle adds up to 9, and everything inside this circle adds up to 5. But we don't know which ones are here, and which ones are here, and which ones are here, because they're all shared. So the one that you should always start with is that the fact they're both 3. So you put in the 3. So now I've done that, I can cross this out. Now I can start filling out the rest of the information. Since I know there's 3 people here and 9 people play football, then this one has to be 9 minus 3 over here, because 9 people play football in total. So if I put in a 6 here, this circle now adds up to 9. So that's how many people play football. So now I can cross that one out too. Same for cricket. I know 3 people play cricket here, and there's 5 in total, so this one must be 5 minus 3, which is 2. And now I can cross that one out as well. So now I know in total we've got 9 6 plus 3 plus 2 people who play football and cricket between themselves. So if you add them all up, that gives you 9 plus 2, which is 11. So that means in my class of 40, there's 11 people I've accounted for. So everyone I haven't accounted for would be outside over here, which is 40 minus 11, which would give me 29 people. So, and that's it. Now I've done this, the questions are very easy. So what's the probability if you're not playing cricket? Well, there's 40 people in my class in total. And what's the chance that you don't play cricket? Well, either it's people here or people here. So the people who only play football and the people who play neither. And that's 35 over 40 over there. So that was pretty simple to do, nothing too hard to understand there. And that's pretty much it for that. And then we have the next question, which is what's the probability that they're neither F or C? Well, again, there's 40 students in total, and the ones who play nothing are this lot here. So the answer to that is just 29 over 40. And that's pretty much all you have to do in these questions. The main part is just be careful, don't make that a 9, don't make that a 5 just because you saw these numbers here. Always start with the one which is both, or the one that isn't common for everything, and then from that, once I figured out this, then I was able to figure out this part, and then I was able to figure out this part, and then finally the whole thing. So just start with the one which is usually both or everything in the middle, and that will make it much, much easier for you to answer the question. Cool. So since we've done that one, we can now carry on with this question and show you a slightly harder one. So there's another circle here. So let's say now we've introduced another sport, which is golf. And now I wanted you to find out what's the probability that the person plays, let's say, football only. What's the probability that he does not play golf? And let's say the last question would be they don't play any of these sports, so plays none of them. Okay, so again, it's actually the same concept of the one we literally just did. All you got to do is fill out this graph with the numbers you've got. So like we said before, we want to do the same thing. Start with the one which is all and put that straight into the middle. So if we do that for all, we'll get 2 right in the middle, and that's for sure. There's 3 people who play football, golf, and cricket. So since I've done that one, I can cross this out. And now let's take a look at cricket and golf. So once I've done the one with all 3, now let's do the ones which are sets of 2s. So people who play cricket and golf, there are 10 people who play cricket and golf. So that means, where's cricket and golf? Where does that intersect? That's this part here. So that means we've already got 2 people there. So 8 people must be playing that. So now this adds up to 10, just like we wanted. So now I can cross that off. For football and golf, we have 8 people. So here we've already got 2. So we'll make that a 6. That means that this adds up to 8. We can cross that off now. Football and cricket is 6. So now you can see here, we've only got 2. So to patch that up, we have to put in a 4. And that makes that up. Now we've done all the ones with sets of 2s, we can do all the sets of 1s. So 17 people play football. So if we add all of that up, we've got 4, 6, and 2 already in football, which means 12 people, which means to finish off, we need a total of 5 there. For cricket, 4, 2, and 8 again adds up to 14. So this time we've got 14, so that means only 3 people can be playing cricket over there. And again, that adds up to the right number. And the rest play golf. So 2 plus 8 is 10, plus 6 is 16. And the ones which are left would be 7. And that makes up everything. So we've accounted for golf. And if you add up all these circles, you'll see that it all adds up. So now we've got the people who are outside. So if you add up everything, 5 plus 4 plus 3 plus 6 plus 2 plus 8 plus 7 equals something. So that would be, if I just try to do that, there's 17 people who play football, plus 3 is 20, 28, and 35. So there's 35 people in total inside. So that means here we should be 100 minus 35, which is 65 people play none of them. So if you had to answer this question, how many people play football only? Well, that would be these 5 people here. So how many people in the total? There's 100. How many people play football only? 5 out of 100. How many people do not play golf? Well, anyone inside this circle plays golf, and anyone outside this circle does not play golf. That means the ones in the squares are not playing golf because outside of this circle over here, which I've got. So 5 plus 4 is 9, plus 3 is 12, plus 65 is 77. So 77 out of 100 people do not play golf. And how many people play none of the three? Well, that's everyone who's outside the circle, which would be this one here, and that would be 65 over 100. So the kind of questions you'll get will either be usually these two circle Venn diagrams or three circle Venn diagrams, and you'll be given a bunch of information. Just remember, start with the one which has information about all three, then all two, then one of them, and then just subtract to find the one outside. And actually, these questions are pretty simple if you just follow that. Same thing for this one. Start with the one which has all two in it, then start with the ones which are just single ones, and then find the one outside. So if you, as long as you do that, you fill that in first, and then you just check up how the thing should add up, then it all kind of works out. So for Venn diagrams, actually, that's pretty much it. It's a pretty short topic, and hopefully there's not too much that you need to take a look at that to understand. So let's now move on to mutually exclusive and independent events. Okay, so next up, we're going to take a look at mutually exclusive and independent events. And these are two things which people I've seen get wrong quite often. So people often mix up the definitions for mutually exclusive and independence. So I'm going to try and show you how the two are different in this part over here. So with mutually exclusive things, what I'm trying to say is basically if event A occurs, then that means B can't have occurred. So that's why you can see that these two Venn diagrams here are separate and they're not overlapping. If they weren't mutually exclusive, then they'd have this overlap where this middle part would be shaded in. And that means that in this part, for example, if A has occurred, then B has also occurred. But if they're mutually exclusive, it means if something happened in A, you can see that anything I have in A can never be in B. You can see they're always separate. There's no overlap. So being mutually exclusive means that, yeah, if A doesn't happen, B can't happen, and same for if B happens, A can't happen. So the way you write that in the probability notation is the probability of A or B is equal to the probability of A plus the probability of B. And why is that? And that's because our two circles are separate. So if you want the two probabilities, we just add up these two circles together. And that's pretty much it. That's mutually exclusive events. So independent events means that if A occurs, then it has no bearing on B. So for example, if I go shopping today, it has no bearing on my friend in another country going to bed at a certain time. Those two events are completely independent. So any events which have nothing to do with each other, don't affect each other, are independent events. So something which is not independent would be if it's raining, I took my umbrella. Usually if I take my umbrella, then it's probably dependent on the fact it's raining or not. So independent events are where event A has no effect whatsoever on event B, and hence, if you want to find the probability of A happening and B happening, because these two don't have an effect on each other, the probabilities are just the probability of A times the probability of B. That's quite simply it. So these are the two rules you need to know. Mutually exclusive, PA plus PB, and independent is PA times PB. So hopefully that clears up how the two are different. So let's take a look at a couple of examples of how we solve questions like these. So we can also use this idea here to prove independence, and we'll get onto that later. So let's say we had a question like this where I said the probability of A was 0.3, probability of B was 0.4, and someone said find the probability of A or B. Well, quite simply, the probability of A or B would be this probability plus this probability, since they're mutually exclusive events, and we said A or B is just those two added together. So this would just quite simply be 0.3 plus 0.4, giving us 0.7. And therefore we can tell that the outside part should be 0.3 because 1 minus 0.7 is 0.3. So the probability of A but not B, well, what is that probability going to be there? The probability of A happening but not B. Now the thing is they're mutually exclusive events. So A but not B means that pretty much it's the same as having the probability of A, because in this case we know they're mutually exclusive. So B happening has no effect on A happening. So probability of A but not B is basically just the probability of A, which is 0.3. And you can see that here, the probability of A but not B is 0.3, since there's no way of B overlapping with that. If I had an overlap of A and B like that, then there'd be some overlap and then we'd have to take care of that. But because they're mutually exclusive, there's no overlap over there. So that part is quite simply just 0.3. Now the probability of neither A nor B is the probability we've already found over 0.3 down there. because neither A happening nor this happening, well, that's just this one out here, 0.3. So I hope that's a simple type of question to understand. Let's take another look at another kind of question. So let's say A and B are independent, and we say the probability of A is 0.3, the probability of B is 0.2. So what is the probability of A and B? Well, normally, because we know this is independent, we can quite simply just multiply this times this to find A and B, since that's our rule for independence. So here it is 0.3 times 0.2, which should be 0.06, I believe. And that's going to be your answer for the probability of A and B. That's probability of A and B, that one there. And that's because they're two independent events. So that's why we can just multiply these two numbers together. So those are just two simple examples to show you how mutually exclusive things can be used, and here how independent things can be used. So now let's actually move on to a slightly bigger question on something over here. So let's say I give you this Venn diagram and I ask you, can you find the probability of A happening, or B happening, or both happening? So probability A or B or both would be the probability of A, the probability of A happening, or B happening, or both, so everything in between. So basically what we're trying to say is just everything in these circles here. So it's quite simply just going to be pi A, just 4 plus 6 plus 7 plus 10 divided by how many we have in total in this question. So in total, how many different things do we have? Let's add that up. So we've got, this is 4 plus 6 is 10, 17, 27, 37, 52. So that's just 52. So the answer for this one will be 27 over 52. That's the probability A or B of both happening. And the next kind of question you often get asked is reading A and B, so these are just probabilities of reading books A, B, and C, are those probabilities, or are A and B independent of each other? And the way you solve these kinds of questions is quite simply, you need to find the probability of A, then you need to find the probability of B. So to do this, we have to find probability of A. So that's just 4 plus 6, because that's all we've got in that circle. And we just have to take that and we divide that by the total number. So 4 plus 6 is 10 over 52. That's going to be probability of A. Then you find probability of B next. So the probability of B would be 6 plus 7 plus 10, which gives us 23 over 52. And once you've got the probability of A and the probability of B, well, the thing is, if you take a look at the diagram itself, this represents the probability of A and B. So the probability of A and B according to our diagram should be 6 over 52. However, we can check this, because if we know that they're independent, then P of A times P of B should also give us this equation here. So let's actually put in our numbers for P of A times P of B. That gives us this number, which gives us 230 over 52, which squared. So I'll just check that in my calculator. That gives us a value of 2,704. And these two numbers are not the same as each other. So these two numbers, since they're not equal to each other, we can say they are not independent. So they are not independent events. If they were the same as each other, then you would say they're independent. So whenever a question asks you, are these two events independent, what you should do is find probability of A, find probability of B, multiply them together to get a certain number, and then from the graph, read what the actual probability of A and B shows us, and then if that number you got matches the number you got here, then you know the two events are independent. If that's not the case, then unfortunately they are not independent events. And that's all there is to figuring out that kind of question. So I hope that that helps. So now we can move on to the very last part, which is probably the easiest part. So for this question, we're going to take a look at tree diagrams. And you've probably seen these in GCSEs, and they're nothing too difficult in year 1 stats either. So tree diagrams is kind of tell you the outcome of probabilities as they're happening, like one after the other. So like I pulled a ball out of a bag, then another one, then another one. So you just draw more and more trees. So I guess the easiest way to kind of go through this is just go through examples. So a bag has 8 blue counters and 7 yellow counters. So straight away I can say there are 15 counters in total. Let's write that as a note. And then we know that the probability of both being green, we want to find the probability of both being green and the probability that they're different colors. Well, before we start, let's say that we have to take this. So in this question, let's say I haven't written it down, but you're supposed to take 2 balls. So you take first pick, then after that you take another pick, and you don't replace the balls after each other. That's important. So on my first pick, what's going to happen? What's the probability that I pick a blue counter? My first one, I just read the question doesn't make sense. This can't be green. This has got to be blue. We only have blue and yellow counters. So what's the probability that we have a blue counter, and what's the probability we have a yellow counter first? So probability of a blue counter is out of 15, we have 8 blue counters and we have 7 over 15 yellow counters. Now, if we already picked a blue counter in our first pick, that means there's only 7 blue counters left, and because we picked one counter, there's only 14 things left. Here there's only 14 counters left, but then there's still 7 yellow counters. In the case at the bottom, if there's 7 over 15 yellow counters and we pick a yellow counter, then there's only 14 counters left and only 6 are yellow. And here there'd be only 14 counters left, but all 8 would be blue. So that would kind of give us our tree diagram there. And if someone asked us how to solve it now, we could quite easily solve part A, that what's the chance that both are blue? Well, for that, we just travel along this part of the graph and this part of the graph, which are corresponding to these two probabilities. So we just say 8 times 15 times 7 over 14, which is 56 over whatever that is in my calculator again. 15 times 14, 210. So that's the answer for your blue counters. And what's the probability that they're different colors? Well, there's 2 ways they can be different colors. I could either pick blue, then yellow, which means I have to use these 2, or I can pick yellow and blue, which means I use these 2. So there's 2 different ways that can happen. So I do 8 over 15 times 7 over 14 plus, so that was taking this part here, and now I'm going to take this part here. That will give me 7 over 15 times 8 over 14. So that, if I do put that together, you need 56 again over 210 plus 56 over 210, which is equal to 112 over 210. So that's the answer for them being different colors. And in probability, that's pretty much all you need to know for year 1. So the main things you need to really understand, if I have to kind of go through all the chapters we've done again, would probably be just understand from the beginning what the different parts are and how to find single kind of probabilities. But I think that's a part that everyone's fairly comfortable with. The key part that you really need to understand is the Venn diagrams. So if someone asks you to shade Venn diagrams in or put in the different numbers like you've done here, you need to be comfortable with that, with 2 or 3 circles. Apart from that, make sure you know how to do mutually exclusive and independent events. These are the different kind of questions you can be asked. These 2 are the easiest type. This is the kind of type you can expect in year 1 stats for question 3. So something like, are these 2 really independent? What's the probability of A or B or both? And that should be okay. Usually in your exams, year 2 stats does build upon probability quite a bit. So a lot of your questions will probably be from that chapter, but for like the first parts of your questions in your paper, this is the kind of stuff that you can expect. And then finally, the tree diagram stuff is not very difficult either. And again, in year 2 stats, I'll build upon that. But for year 1, it should be fairly simple. There's not too much content and it's fairly easy to kind of go through. So hopefully that should be good enough. And then for our next video, we'll probably be taking a look at statistical distributions. And yeah, just if you found this video helpful for understanding probabilities, please just share it with your friends so I can continue making more in this series. Thanks a lot, and I'll see you in the next video.